In this video, we're going to be looking at an example of a hypothesis test for two proportions from independent samples, and I'm going to show you how to reconcile the results of that with a confidence interval. But before we dig into the particular example that I have, I wanted to mention a few things. For example, when you're doing a hypothesis test for two proportions, there's always more than one way to say what it is that you're trying to say. And so, in other words, on this particular slide here, I'm using the Greek letter theta as a stand-in for a parameter of some kind. So it could be a population mean, mu. It could be a population proportion, p. It could be a population standard deviation, sigma, something like that. And what I'm saying effectively is that, typically our null hypothesis is a claim of equality. So here we have it represented as theta 1 equals theta 2. And that could also be phrased a different way. We could say theta 1 minus theta 2 is equal to 0. Likewise, theta 1 greater than theta 2. You could say the same thing by saying theta 1 minus theta 2 is greater than 0, and so on. And because the order of the samples is arbitrary, if you're doing a directional test, that is a left-tailed test or a right-tailed test, you can also run those tests two ways. And so, for example, you could run a test as theta 1 greater than theta 2, but the same test could be run saying theta 2 is less than theta 1. And so what I'm saying in a roundabout fashion is that when you read the problems here, you have to be careful, more careful than usual. Sometimes they will tell you directly what the order of subtraction is supposed to be. Sometimes they don't. In any case, you have to be watching very carefully and making sure that what you're doing is going to mesh with what the book is asking for. And you're probably going to struggle with it at the beginning. Everyone does, but it is doable. And so we want to show you a particular example, and let's take a look at it first. We're going to be using problem number 24 here that you can see on the screen. And as an aside, before I forget to mention it, this situation here has independent samples. I hope that would be fairly clear when you're reading through it. We don't actually do proportions with dependent samples in our course. That material is omitted. It's in the text if you want to read about it, but we don't do that. We're just doing independent samples for proportions. We do dependent samples for other parameters, population means, for example, but for proportions, it's omitted. Anyway, let's see what this one says here. It says researchers at Harris Interactive wondered if there was a difference between males and females in regard to whether they typically buy name brand or store brand products. They asked a random sample of males and females the following question. For each of the following types of products, please indicate whether you typically buy name brand products or store brand products. Among the 1,104 males that were surveyed, 343 indicated that they buy name brand over-the-counter drugs. Among the 1,172 females surveyed, 295 indicated that they buy name brand over-the-counter drugs. Does the evidence suggest that a lower proportion of females buy name brand over-the-counter drugs? Okay, so we're going to get to that in a bit. Notice in part A here they're asking us why can we do what we're about to do? So in other words, there's some conditions that have to be satisfied. We want to take a quick look at that. Real quick before I get to part A, this section is a very heavy section in terms of notation. There is a lot of notation. And if you're not understanding what each of the items means, it makes it much harder than it really needs to be. So just to make sure you're tracking us here, take a look at what we have on this slide. Ask yourself, how would I read this over the telephone? Now, you probably remember from previous chapter that when you have a P with a little chevron above it like that, that we read that as P hat. And so if I was reading this slide to you here over the telephone, I would read that as P sub 1 hat is equal to X sub 1 over N sub 1. And P sub 2 hat is equal to X sub 2 over N sub 2. So what is P sub 1 hat? Well, that's the sample proportion from sample 1. And X sub 1 is the number of individuals in that sample with some characteristic of interest. And N sub 1 is the size of that sample. Likewise, P sub 2 hat is the proportion from sample 2 proportion. And X sub 2 is the number of individuals in sample 2 that have a characteristic of interest, and N sub 2 is the size of sample 2. Now the order of the samples is arbitrary, right? So you can interchange them as long as you keep everything straight. It doesn't make a difference. But let's see what else we need to know in order to answer part A. We have two conditions, as you can read here. First, we need to make sure that we're not exceeding 5% of the population with our samples. When you do that, you lose independence. And for that reason, we try not to oversample. And for the problems that we're going to be working on, in truth, you're not going to really have to worry about checking that particular condition. It's generally going to be assumed to be true. The condition that you would have to check, though, is that the data is normal enough. And so that is these two conditions you can see towards the top of this slide here. Now, usually, if you're answering a question, or if you're answering something like part A here, where they're asking you to verify that we can run the test, what they're really saying is they want you to test whether the data is normal enough or not. And so I'm not going to write down a lot of detail for that, but I would, I would have something from my calculator that I would get. So I'd like to show you how to get that. Now, when you're doing this portion, you can do a whole lot of typing on the calculator. And so I'm going to show you how I would work it out. It's maybe a little bit slicker. I'm not saying you have to do it my way, but it definitely can save you a few keystrokes. So here's what I'm going to do. It turns out that if you are careless when you're working on these problems and you propagate a round-off error, you can really make garbage in, garbage out. So you really want to try hard not to propagate a round-off error, and at the same time you want to minimize what it is that you're typing. And so you can let the calculator help with that as follows. If you recall, the proportion, the sample proportion from the men would be 343 divided by 1104, or 1104, okay? Now, instead of typing that value over and over and over again, or instead of typing a rounded version of it from that decimal you can see right there, it's much nicer if you just let the calculator do it for you. You can store it in a memory register. I'm just going to use letter A. You can use any of the letters that you see there in green on the calculator keypad. And I've got it saved now. And it may not be obvious that it's saved, but it is, because when I call up the letter A, you can see that I get that same value back. So I can store both of those sample proportions in that way, and that will save me a lot of typing. And so I'm going to do that. So for the women, it was 295 over 1172. And I'm just going to put it right in alpha B. And so it's there, and as you can see, I have the decimal value that I need. Okay, so checking normality. So for the men, we want to take the sample size times the sample proportion times 1 minus the sample proportion. So we would take 1104 times A times 1 minus A. And in that way, we get our answer to full precision with minimal typing. There's the value. I would write that down. And then likewise for the women. So the sample size was 1172. We're going to multiply that by sample proportion times 1 minus the sample proportion. There you go. There's the value for the women. Both of those are greater than 10. And so I would say, well, our data is normal enough. Let's put that down. So I've recorded both of those values, and again, since they're both larger than 10, we're good to go. Data is normal enough. Let's see what's next. Part B is asking, what are the null and alternative hypotheses? And so if you read the main write-up carefully, you'll notice, hopefully, that the very last sentence is the one that we want. It's what tells us our alternative hypothesis. It says, does the evidence suggest a lower proportion of females buy name brand over-the-counter drugs? So let's translate that to an alternative hypothesis. I've introduced a little bit of notation down here at the bottom. Notice P sub 1 is the population proportion of males who prefer brand name over-the-counter drugs, and P sub 2 is the population proportion of females who prefer brand name over-the-counter drugs. And so we want to translate what we saw in the book to an alternative hypothesis and a null hypothesis using that notation. Now we're sort of dodging a bullet here a little bit if you read carefully, because we use the males for sample 1 and we use the females for sample 2. We could change that around if we wanted to. You get the same result as long as you do it correctly, but when you look at the calculator and you see the way the calculator works, you'll see why I'm doing what I'm doing here. So let me show you real briefly. The particular test that we use here is the 2 proportion z-test. It's a built-in function, and we definitely want to use this because the round-off error can be horrendous with this type of problem if you turn away from using this. We don't want you calculating the test statistic or anything here by hand if it can be avoided. So anyway, it's number 6 on this calculator menu, and you'll notice when you look at the test that the hypothesis, the alternative hypothesis, is not really flexible. So in other words, when you write the alternative hypothesis, or when you put it into the calculator, P sub 1 is going to be on the left. And so what the calculator really wants you to decide is what's going to go on the right. Is it going to be not equals P sub 2, or is it going to be less than P sub 2, or is it going to be greater than P sub 2? So knowing that, as I'm writing this down, I'm thinking, okay, wait a minute, I had the males as sample 1. I just kind of went with that because it was listed first in the problem. And I had the females as sample 2, but I want to make sure that this is going to come out. And so, especially with the confusion that's possible here. So that's why I'm doing what I'm doing. Let's go back and take a look again here. So females less than males can be restated as males greater than females. And I want that because I can't have females on the left-hand side of my alternative hypothesis unless I change the order of my samples. That's what I'm trying to say here. And so I rewrote this so that what I had before is going to work with what I have in the calculator without having to think too much about it. Anyway, my alternative hypothesis, the one that really is of interest to us, would be P sub 1 greater than P sub 2, or if you want to use a subtraction, you could say P sub 1 minus P sub 2 greater than 0. And so at that point, we're ready to look at part C. Now notice that the direction of subtraction is supplied there in part C. And MyLab used to have a conflict when these problems were done not the way that the book did them. In other words, it wasn't very flexible. It's my understanding now that MyLab has been programmed to permit the dual approaches. So you should not have a problem, but I'm going to stick to what I have there in the book, even though that is not exactly what I'm going to be testing. It's the same distribution because of the symmetry. Anyway, here's the thing. It says, describe the sampling distribution of p hat sub female minus p hat sub male. Draw a normal model with the area representing the p-value shaded for this hypothesis test. Okay, so they want us to obviously run the test, otherwise we'd have a very hard time getting the p-value. And they want some other things from us. Let's see what we need to know in order to answer this. As you can read here on the slide, when the conditions that we previously tested are satisfied, that tells us that the sampling distribution is approximately normal, and the mean of the sampling distribution is going to be P sub 1 minus P sub 2, or P sub 2 minus P sub 1. It actually doesn't matter. And notice that when we do a hypothesis test like this, we assume that the null hypothesis is true. And so that means that we are effectively assuming that P sub 1 is equal to P sub 2. And so obviously if you subtract them, you get 0. So in response to part C, the first thing we would put down to help describe the sampling distribution would be the mean. Let's write that down. So the mean of the sampling distribution again is 0. And as far as the standard deviation, we need you to use the formula that you see here. It's in the lower right-hand corner of the slide there. This is a little bit confusing. If you asked me to read that formula to you over the telephone, I would read it as sigma sub p sub 1 hat minus p sub 2 hat. And the thing is, when we calculate this, it turns out that the sample proportions, in other words p sub 1 hat and p sub 2 hat, are going to be used as estimators for the population proportions. So in other words, in that formula right there, you see p sub 1 and p sub 2, but we're not going to be using p sub 1 and p sub 2. We're going to use p sub 1 hat and p sub 2 hat. And so we definitely want to be able to give you a value for this, and so we're going to get it from the calculator, and we're going to be using what we had previously stored in those memory registers in order to speed the calculation. Let's go take a look. So I need to get out of here, and I need to open up a radical. Big radical with lots of parentheses. Now you have to be really careful about opening and closing the parentheses here. It's very easy to get it wrong if you're careless. So watch carefully what I'm going to do. For the first quantity, you're supposed to take, well, you're going to need two openers, let's put it that way. And the quantity is going to be p sub 1 hat times 1 minus p sub 1 hat, and then you're going to divide that whole thing by the sample size. So p sub 1 hat was in alpha A, and we're going to multiply that by 1 minus that. And then we're going to close that and divide that by the sample size, which was 1104. Close that again. And then we're going to add the same thing with the second sample. And so that would be alpha B times 1 minus alpha B. Close quantity, divided by the sample size, 1172. Close that quantity, and then close the radical. So lots of openers, lots of closers. The calculator can help you a bit, but look carefully at what we did. Here's the value. And so, I think probably 4 places would be sufficient for that. It is a very small value. It is very sensitive to round-off error as well. So let's put this down. So I have that down, and then I'm ready to do the rest of that, which is to run the test and then to draw the picture that they were asking for. Okay, we're ready to run the test. So go to the stat menu, go to the test submenu, and we're looking for the 2 proportion z-test, number 6 on this menu. Our inputs are as follows. And as we said, for the alternative hypothesis, we are testing whether the proportion of women is less, and so translated to what the calculator needs, it would be p sub 1 greater than p sub 2. Press enter to affirm that, and then you can calculate. There's our results right there. So we're going to need to jot that down, and we're going to need a picture. Now the whole thing, you don't need to write down everything here. We need the test statistic as well as the p-value, and that should be sufficient. So they were asking me in part C to draw the distribution, which I did, and I've provided appropriate labeling there. So I have the mean and the standard deviation. The p-value, if you recall, is the area of the tail to whatever side you're testing on from where the test statistic is located. And it represents the probability of obtaining a test statistic more extreme than the one we got, assuming that the null hypothesis is true. So the test statistic was 3.13, and the p-value was about 0.000871, and so on. And so it's very far up in the right tail, and that's the picture right there. Let's see what else they want. So in part D, they're asking that we would determine the p-value based on the model from part C, which we did, and we gave you the value. As far as interpreting the p-value, that's part E, and it's like we just said, the p-value is the probability of obtaining a test statistic more extreme, in other words, further to the right of the one we obtained, assuming that the null hypothesis is true. And so we can jot that down for you. So our response to part D is shown there on the screen. We've written down the p-value. Actually, I wrote it down as part of my response to part C, but anyway, let's answer part E. It's asking again, what's the significance of the p-value? So let me jot that down. So again, the p-value is the probability of obtaining a test statistic more extreme, or in this case, further to the right-hand side. That's what RHS is short for, is right-hand side, than what we obtained, assuming that the null hypothesis is true. Let's see what's next. And finally, after a very long period of time, we come to part F, which says, based on the p-value, what does the sample evidence suggest? That is, what is the conclusion of the hypothesis test? Assume alpha is 0.05. Well, you probably recall that when the p-value is less than alpha, we reject the null. And so we're going to do that in this case. And the null hypothesis was a claim of equality. That means we're also affirming the alternative hypothesis, which was that the proportion of females was less. So let's state that, and we'll be done. So once again, since the p-value is less than alpha, we reject the null. And the practical conclusion is that the evidence we have shows that the proportion of females who prefer to purchase brand name over-the-counter drugs is lower than the proportion of males. Very briefly, a couple of quick final thoughts. It is possible to address test questions, hypothesis test questions, with a confidence interval. And so that is one approach that could be taken here. I'll show you that very briefly. And also, if you'd run the test in the other direction, you get the same result, effectively, same p-value that is, but your test statistic would be on the other side of the distribution, and it would have the opposite sign. So take a quick look at that. So notice what I've done here is I've swapped the samples. So I have the women in sample 1 and I have the men in sample 2. And I've also changed the direction of the alternative hypothesis. So here I'm testing p sub 1 less than p sub 2, which is the same thing once the samples have been swapped. So here's the result. And as you can see, it's identical. I mean, well, almost. The test statistic is negative. So it's on the left-hand side of the distribution, and the p-value is the same. If you were to draw the picture that corresponds to this version of the test, you'd be shading the left tail for the p-value instead of the right tail. Now, as far as a confidence interval is concerned, in order to run the confidence interval, you need to go back to the stat menu, you go to the test submenu, and we're looking for a 2 proportion z interval. It's buried a little bit in the menu. It's letter B here, so you can just go up to get that. And if you run it, you can see that everything is already in place, and actually it's the backwards version because we just ran the backwards version. Everything is there and it's good to go, and the confidence level is correct because remember that alpha, the level of significance alpha is related to the confidence interval confidence level, because the confidence level is 1 minus alpha. So in other words, if your alpha is 0.05, then your confidence level should be 0.95, as you see here. And when you run this, the most important thing to notice is that both endpoints of the confidence interval are negative. And so 0 is not contained in this confidence interval, and so for that reason we would be rejecting the null. And that's what we were saying on this slide over here, is if you want to square these two approaches, that's really what you're looking for in this case, is whether or not the confidence interval contains 0. If it contains it, that suggests that the null is plausible. If it doesn't contain it, that suggests that we're however percent, 95% confident, like in this case, that the null hypothesis is not plausible. Anyway, I hope that helps, and if you have any questions, feel free to drop me a line. I have another example for you in a different video.